So for the review set, excuse me, review set, week 3 for work / energy. I suggest numbers 11 through 25, 26 through 33, 35, A and B, 36, A and B, and 37 through 45. That's why I would suggest that we're not going to work on all of that today, but we'll do some of that today. And of course, I'll have you guys do some for tonight. And then for review set, week 3, for momentum / collisions. We'll see what would be good ones for that one. So I'll stop sharing this for a little bit. Let me share the whole screen. And I would definitely suggest 6, to 36. We'll probably explore 37 through 40. Through 44, definitely 45 through 49. And 50 through 52. Then problem solving, don't want to do any of the nasty ones, the collisions. But I believe 57, yeah, like something like 64, I don't want to do with you guys. That's gonna be a little much, I think. I probably would say 57 through perhaps 62 might be good. Just trying to see if the other ones are good here. Yeah, we'll say that. So I'll write this on the whiteboard. So go back and share the whiteboard again. So I would say number 6 through 30, 6, 37 through 40, 41 through 44, 45 through 49, 50 through 52, and 57 through 62. So those would be the problems I would suggest that we do. So let's actually work through some of the multiple choice ones today. I'll do maybe a handful and have guys go back in groups. So I'll probably spend a few minutes talking about a handful of multiple choice questions for energy and a handful for momentum. And again, I'll put this up in Schoology as well, so don't worry about that if you didn't get it all, but or you can take a picture with your phone if you like, but I'm recording this too. Okay, let's go back to sharing the screen again. Here we go. So I'm going back to the work and energy review set. And let's start with number 11. So I'll probably do 11 through 16 here. And then maybe I'll have you guys do 17 to 25 in small groups. So let's look at this one. Assume that G is 10 meters per second squared, okay? So 1,200 kilogram car and 24 kilogram car lifted to the same height at constant speed in an auto service station. Lifting the more massive car requires, well, remember, force equals, energy or work equals force times distance, and force is ma. So clearly there's more mass. So remember, again, energy, or let's call it work, and force is mass times acceleration times distance. So clearly the car is 24 kilograms, has twice much mass. So it can take twice as much work. An arrow is run back, so 50 joules of potential energy stored in the stretch bow and string. When released, the arrow will have kinetic energy of, well, you want to conserve it. So it should be exactly the same. So it's A, or it's conservation.
Mr. E.
Yeah, go ahead.
For number 11, isn't the acceleration 0 because it's going at a constant speed?
Oh, I didn't see that. Oh, so the forces are the same. Well, actually, hold on a sec. Yeah, because it's the applied force, right? Lifting the more massive car. No, you're right. I was thinking weight due to gravity. Yeah, you're right. That's a trick question. Should have saw that. So that is correct. So you have no acceleration, so no force. Yeah, so that's going to be the same. You're 100% correct. Okay, now look out for that. Okay, so 13. Child lifts the box up from the floor. The child then carries the box with constant speed to the other side of the room, puts the box down. How much work does he do on the box? Well, so 0 joules. His constant speed. Again, no acceleration. 14. 1,000 kilogram car is moving 40 kilometers per hour when the driver slams the brakes and skids to a stop. With locked brakes over a distance of 20 meters. How far the car skid with locked brakes? It was traveling 120. So how far the car skid? Hold on, but you have 40 kilometers per hour. Oh, so you're doing a comparison. Got it. Got it. Okay. So, yeah. What you want to do is you can kind of just do a comparison, I guess, because you remember acceleration is your final velocity minus initial velocity divided by time. So I'd imagine that if you're, and you're probably conserving, hold on, just need to think about this one here. You probably could, the more I think about it, I think it's a 9-fold increase. And the reason I'm saying that is because V squared equals V0 squared plus 2A times D. And so, and obviously you're coming to rest. So what happens is that D and V actually are in a quadratic relationship. So I don't think you have to do any calculation. I think you just have to realize that if you triple the velocity, or triple the speed, goes up 9 times. That's 180. So it's kind of like the driver's test you guys take. Like you're told if you're going twice as fast, your stopping distance is actually 4 times as much. So like for example, if your braking distance is 100 meters at going 30 miles per hour, then if you go 6 miles per hour, now it's 400 meters. So I think that's what's going on. 14. I think it's just you don't really actually have to go through the motion of solving it. It's just more doing a comparison. So I believe 14 is going to be E for that one. For 15, the platform diver weighs 500 newtons. She steps off the diving board and is elevated to a height of 10 meters above the water. The diver will possess blank joules of kinetic energy when she hits. So right now, we kind of want to figure out what her, I guess her potential energy, but right now her weight is, weight's mg and it's 500 newtons. So right now she has 100% potential energy. The potential energy right now is going to be 500 times 10 is 5,000. And the kinetic energy will just be the same on the way down because you're conserving it. So that's why it's going to be D for 15. So 15 is going to also be conservation of energy for that one. So those are kind of multiple choice questions I could ask. And if I find 16, they'll have you guys do a little practice. A ball is projected into the air with 100 joules kinetic energy. The kinetic energy is transformed to gravitational potential on the path towards the peak of its trajectory. So when it gets to the peak, where it's momentarily stopped, so the kinetic energy is 0 because 0 velocity. When the ball returns to its original height, its kinetic energy is blank joules. Do you consider the effects? I don't know if I'll ask that one because we haven't really done stuff like that. But if there is air resistance, you are kind of losing. So what happens is that there is so you throw it into the air, and then there's air resistance kind of working against it. So I guess as your kinetic energy is going to be less because it's impacting. You're losing some energy to non-conservative work. So my guess is that's probably what we're going to experience with that one. Let me double check the answer key. So remember, the answer keys you actually could find if we go to the physics classroom. And I'll put this link up in Schoology as well. It'll be on a Thursday night homework. But yeah, if we go work in energy, click on all. So again, I'll share this link with you guys. And we go directly to number 16. Yep, it's A. And look at the other ones here. 15, we did say D. 14, we did say E. 13, we did say A, constant speed. 12, we did say A, it's conserved. 11, oh, okay, so I was right. It was twice as much. So interestingly, actually, yeah, you're doing the weight due to gravity. Yeah, so so you're moving. So going back to 13 again, because I don't want to confuse you guys. So a child lifts the box up from the floor. The child then carries the box at constant speed to the other side of the room and puts the box down. How much work does he do on the box while walking across the floor at constant speed? So the box itself, so the work that you do on the box was 0. But here, the lift has to work against gravity. So that does seem a little confusing though. So let me look at it one more time. I guess you could say for 13, how much does it do? Yeah, because I guess the height stays the same also. While you're walking across forward here, I think the height changes. I think that's probably why so it's kind of like using MGH in a way. Yeah, so anyway, let's have you guys try some practice problems now. So I'll have you guys do 17 through 25. That's 9 problems. I'll give you guys about 10 minutes to do that. Then we'll come back. We'll talk a little about momentum and then we'll wrap it up for today. So again, you guys are doing 17 through 25 of the work and energy review set. 17 through 25. And I will put you guys in breakout rooms right now.